So these are the review slides for Organic 2 Spring 2017 for Exam 4. So with that, so we're going to go over the free answer part. Right, so there's going to be a predict the reagents section. Right, so you need to know what the transformation is. So like this first one here, right, we're going from an alkyne to a cis double bond, right? So the hydrogens are on the same side. So we need to know what does the cis, right? So we're putting the hydrogens on the same side, so it has to be some sort of hydrogenation, but we're not going all the way to the single bond, so it ends up being a poison catalyst, so something like palladium with barium sulfate or Lindlar catalyst or something like that. So it ends up being B. Okay. Now for here, right? So with that we're taking benzene and putting bromine on it. So HBr isn't going to work because we would end up busting apart the benzene. Okay, bromine also isn't going to work because it's not activated. So what we end up having to do is put in a Lewis acid here. So bromine plus FeBr3. So it ends up being F there. So for this one, predict the starting material. So what are you going to need in order to be able to make this molecule? And I'll tell you if it's either a Diels-Alder or a oxidative cleavage here. So with that, and so for here with the Diels-Alder, right? So here's the 6-membered ring, right? So the diene is going to be these 4 carbons here, right? And the dienophile is going to be those 2 carbons there. Okay, so this one ends up, the diene just looks like this, right? There's nothing hanging off of it. The dienophile, right? It's a double bond. Okay, but notice how these groups are both on wedges. Okay, so that means they're going to be hanging off on the same side of the alkene. So it ends up looking like CH3. Okay, and if you want to put in the hydrogens, that's fine. So with that, so there'd be hydrogens on the other side. Okay, so for the ozonolysis, right? So with that, we're not going to get over oxidation. Okay, so with that, so the easiest thing to do for what I've always thought is to just get those get the C double bond O's right next to each other. Okay, so they're facing head to head when you're trying to predict it, and then this is where the double bond is going to be. So instead of putting the O's, you're going to make this into a carbon-carbon double bond. So it ends up like this, right? And then that right there. So this group here ends up being that group there. Okay, so with that. So put those two things together, where they come together, make that into a carbon-carbon bond. Now for this one, right, so for that, you are going to have to write this mechanism, okay, but they work this exact same way, depending on if it's chlorine or bromine, works the same way. So here, right, so we added chlorines here, okay, so chlorine. FeCl3. Okay. Plus HCl. Okay. So first thing, we have to activate our molecule, right? We need to work with the catalyst, right? So this is our catalyst. So usually, first thing's going to happen is one of the molecules is going to react with the catalyst in these mechanisms. So that goes there, but in doing so, it actually rips those electrons away, and so you end up with a Cl plus, and then FeCl4 minus. Okay, so with that, so here I'm going to draw on these hydrogens. Okay, so this double bond is going to come in and attack there, right, to make this. There's still that hydrogen there. Okay, there's also the chlorine. Okay, and I showed you had to put it here, so definitely has to go there. So we need to reestablish the benzene, right, and get rid of that hydrogen. And so what ends up happening is this thing comes and attacks, grabs that hydrogen, those electrons collapse down to remake this. I mean, you end up making FeCl4 like this, but this is just HCl plus FeCl3, and you reset your catalyst. Bromine's going to work the same way. You just have bromines instead of chlorines. Okay, so predict the products. You do need to include the stereochemistry. Okay, so with osmium tetroxide, this is used to regenerate the osmium. You're going to add OHs on either side of the double bond, but they have to be included on the same side. Okay. So let's say they both need to either be wedges or they both need to be dashes. Okay. Either one. Now with this one, right? So okay. That. What you need is you need a CH bond, right next to the ring, right? So there's here and here, right? So with that, you have to look at this carbon and this carbon right there, next to the double bond, I should say, and there is a hydrogen here, right? So we're going to take off one of these, right, and just convert it into a Br. Again, we're going to take that away, convert it into a Br. So ends up being the dibromide product. So there. Okay. Oops. Apparently I picked up the wrong ones. Okay, so let's do this. Okay. So for here, right, we've got you have the Diels-Alder, right? So with that, so this, you know, hydrogens here, right? So you're going to go there, there, right? So you're going to end up making your 6-membered ring, right? But there is this CH2 here, right? So I usually say it goes up. Doesn't matter. It just needs to either be both up or both down. Don't forget your double bond there. Okay. Now, if this is going up, that you have to look at the molecules hanging off your dienophile. If there are any pi bonds, okay, hanging off of it, so like this one here, okay, that's going to go in the opposite direction of this bridgehead here. Okay, so that means if this is going up, that means this is going down. Okay, so that sets the stereochemistry for the other 4, right? So that means this whole group, this whole thing is going down. That means those are going up. Okay, so that means the CH3 is going to be in a wedge. Okay, so it ends up looking like that. Now for this one, okay, so if you have your benzene, concentrated nitric. Okay, so this is because there are lone pairs right next to the ring, right? Ends up being ortho-para directed, right? So it ends up being here, right? Ortho, which is next to it, para, which is across. Okay, so you're going to get both products. You're actually going to get the nitro group here, right? Plus the nitro group here. Okay, so there you go. Okay, so for design and synthesis, so what you need to do is you need to look at the directing groups. Okay, so what you're going to want to do, so before you even think about the chemistry, you have to sort of think about the order in which these have to go on, right? So you have 2 choices. Okay, you can either put the ketone on first and then put on the bromine, or you could put on the bromine, right, and then put on this. Okay, so this one here, this is an ortho, because it's a C double bond O, it's a meta director here, which is so it's 2-way, so it's here and here. The problem is we need that bromine to go there. Now the bromine, right, so it's got lone pairs right next to the ring, right, so it ends up being ortho and pair, which is good because we need to put it there. Okay, so we need to put on the bromine first, which is Br2, Br3, and then put on the carbon group, right? So that's 2 carbons long, so it ends up being the acid chloride, right? So and aluminum chloride here. So with that catalyst. So we can't go through here. So this is the mechanism. So you have to look at how the groups are put on, whether ortho, para, or meta director, to figure out what is the order in which you need to put the groups on, and then figure out how to get them there. So, okay. Okay, so the rest of this way, we're just talking about the reactions, stuff like that. So reactions to no. So here, this is a Wittig reaction, right? So wherever the carbon negative charge is, that is going to directly replace that oxygen, right? The rest of this molecule is effectively unaffected. Okay, so the methyl group over here comes along, right? So the double bond stays there, everything else stays there and stays put. Okay, but that it's just this carbon comes in and replaces that oxygen. Well, I guess the phosphine goes away, triphenylphosphine goes away too, but this whole thing comes in and replaces it. So like that. So for Br, in the presence of peroxide, if it wasn't, there were no peroxides here, right? We'd have to follow Markovnikov's rule, and the bromine would go here because it's the higher numbered side, right? So this is right. So that's tertiary, that's primary. Okay, if it was just HBr, we'd put the bromine here on the tertiary side. But since there's peroxide, you change the mechanism so that the bromine actually goes on first, and so therefore it actually goes on the lower numbered side. Okay. So for KMNO4, right, we kind of mentioned this before. If you have hydrogens right next to the ring, okay, doesn't matter if it's CH, CH2, CH3. Okay, all the rest of the carbons of that chain are going to get ripped away. You're going to be left with just a single carbon that's a carboxylic acid. Okay. Now, if it's quaternary, right, there's no CHs right next to the ring, then that chain is going to be unaffected. Okay. So similar sorts of things with MBS, right? So with that, so if you end up putting in, right, so if you have a hydrogen, a CH, so CH, CH2, CH3, one of those hydrogens is going to get replaced with a bromine. Okay. Again, quaternary carbons aren't affected because they don't have CH bonds. Okay. So here, both of these groups. So this is the Wolff-Kishner. Under this condition, this is Clemenson. So this is under basic conditions. This is under acidic. All they end up doing is they blow away the C double bond out, turns it into a CH2. Okay, it goes away. With hydrogenation, okay, so with that, what you end up doing is you end up taking a double bond down to a single bond, an alkene down to an alkane. Okay. Now we also have the special case where if you have a carbonyl, so C double bond O, right next to that ring, if you have a ketone or an aldehyde right next to that ring, it ends up replacing that with the CH2. Okay, so it ends up similar to this, but it's a special case where this only happens if it's next to the ring. For here, these are some of the alkyne reactions, right? So if you just have regular hydrogenation, you're not going to be able to stop at the alkene, so it ends up going out all the way to the alkane. Okay, but if you poison the catalyst with something like barium sulfate or Lindlar catalyst or something like that, you're going to end up getting the hydrogens on there on the same side. It's going to stop at the cis alkene. Okay. Conversely, if you use sodium and ammonia, lithium is ammonia is another one. You actually end up with the trans double bond. Okay. Now with the ozone and the permanganate, okay, so with ozone and alkenes it makes a difference. For alkynes it doesn't. You're going to slice this in half, and you're going not this one, this one. You're going to slice these in half, okay, and you're going to end up with a carboxylic acid on either end, right? So this carbon has, right, so it's a triple bond coming off of here, so we're going to replace it with 3 CO bonds, and the way that we do that with this carboxylic acid. Now there's a special case where if it's a terminal alkyne, okay, you would end up with formic acid. This can get further oxidized by the ozone or the permanganate into actually CO2 plus water. Okay, it ends up being carbonic acid. So with that, so you end up bubbling out CO2. And so you only one side, the other side is the only thing that remains. Stuff like that. So, okay. Now with oxidations, okay, you're converting, right, CH bonds into new CO bonds, right? So with that, so we can convert this CH bond, the one that's where the carbon, the CO bond is. Okay, so we turn this CO, right, from 1 to 2 CO bonds. Okay, same thing here, right? There's 2. These guys here, you go from 1 CO bond to 3, right? 1, 2, 3. Okay, here there are no CH bonds, right? So this is going to be unaffected. Okay, so with that, so permanganate or chromic acid, the chromium compounds, those are going to do oxidations. Now, if you want to go to just the aldehyde, you can do this with PCC, and that's going to just stop the aldehyde. Okay, so the reactions to note, right? So this is how you put on the different halides onto the benzene. If you want to make a carbon-carbon bond, right? So you have to use something like chloride and aluminum chloride, which will rip this away to make a plus charge here. Okay, either here or here, and then the benzene's going to come and attack and make a bond where that plus charge was, or is, or whatever it is. So usually it's where the chlorine is, that's where the attachment is. Now you do have to be careful with just the regular alkanes, because these, if you were to have a primary carbocation, it would actually, you would do a hydride or methyl shift over to make it more stable, stuff like that. So you do have to worry about rearrangements on this top one. Where you're attaching to a C double bond O, you never get a rearrangements. So do be careful with that. Okay, so again, more things to put on to benzenes, right? So if you want to put a nitro group on here, you can use concentrated nitric acid. Sometimes you can also do nitric and sulfuric acids, aqua regia. So with that, so if you want to do put a sulfonic acid on there, you do SO3 and sulfuric acid. Now with the nitro group, okay, if you hydrogenate this down, it actually turns it into an amine. This is the only way you can get an amine on there, stuff like that. So so you can't go directly from here to here. You have to go through this nitro intermediate to get the nitrogen in place, and then you can replace the oxygen bonds for the NO bonds for NH bonds. So you have to sometimes do that. And again, we talked about CHEM3120 and NBS with earlier. So like that. So now for directing groups, right? So if you have right, so if you have regular alkanes, stuff like that. So these are going to be orthopara, right? Doesn't matter if it's methyl, ethyl, propyl, butyl, cyclobutyl, cyclohexyl, whatever, right? So those are going to be, it's weakly activating, okay? So but they're orthopara. Same goes with these, right? So all the halogens, right? If you have lone pairs right next to the ring, it will be orthopara directing. Now, in a OH, NH, SH, things like that, those are going to be activating, right? So they're going to speed up the reaction. The halides, they're orthopara, but they're actually deactivating because they're electronegative. They're sucking out electron density from the ring, so slowing things down. Okay, and then for here, these are the meta-directors are always end up being withdrawing. But if you have C double bond O right next to the ring, okay, S double bond O, N double bond O, right? So the nitro group, that looks like this if you write it out. Okay, right? This N double bond O makes it meta-directing, but it's also deactivating. C triple bond N, that's another one. So that those are all meta-directors, and they're very deactivating, so they slow things down. Okay, for the Diels-Alder, right? So you're gonna, I usually end up writing the mechanism out, so there to there to there, right? So you don't forget the double bond here, stuff like that. But remember, these are on these methyl groups are on the same side, so they're both going to be either both have wedges or both have dashes. Okay. Now with this one, it becomes a little bit of an issue, right? This CH2, okay. Here, if you're gonna ends up being that CH2 there, if you're gonna move this up, okay, the thing with the pi bonds, okay, so this guy here is going to want to go in the opposite direction. So it's going to want to go down. That means this whole side is down, okay, which means this side, those two hydrogens, right, are going to be up. Okay, so both of these are going to be, if this is on a wedge, that's going to have to be on a dash. And last up, things to note, right? So for osmium, okay, you're going to end up putting OHs across here, okay, but they're going to both be on the same side, so they're both either going to be both wedges or both dashes. Okay, with the osmium under reducing conditions, it's either zinc and acid or dimethyl sulfide, right? So all you got to do is cut that in half, and you're going to put those directly, make those CC double bonds into CO double bonds. Okay, so it ends up being here and here, right? And this hydrogen, right? You make the aldehyde, that's going to be unaffected. Okay, exact same thing happens with the permanganate, but you end up making the aldehyde. Okay, and so this ends up getting converted into the OH. Okay, the aldehyde is still reactive to the KMNO4. Okay, now the pyridates, this is also could be, you can also use sodium pyridate. instead of proiodic acid. This is going to cleave right between carbons that have OH's group right next to each other. Okay, so they have to be right next to each other, and they have to be pointed in roughly the same direction. Okay, so if it's just a regular alkane, no big deal because you get free rotation, right? But if you have, let's say, a ring, right, you're going to need to get those, like both equatorial, or you're going to need to get them at least pointed generally in the same direction, because the proiodate has to come in and grab both of them at the same time to rip them, to do the oxidation, stuff like that. So, so you end up doing this. So it's very similar to the results are very similar to the ozone, but you cleave between, instead of a carbon-carbon double bond, you cleave in between a carbon CO bond, right? And so this ends up just, instead of a CO, you have C double bond O. Okay, and these hydrogens go away. So, like that. Good luck.